Okay, hello everyone, and welcome to today's Hi5 seminar. We have an excellent speaker today coming to us from Iowa State University, John Kelly. He is a professor in psychology and a long-time seeker of knowledge and scientist in spatial perception and virtual environments. So without any further ado, I'm going to turn this over to John. John, you ready to go?
Thanks so much, Adam. Thanks for inviting me here, by the way. It's fun to talk about things that are happening in my lab. Let me share my slides with you. Um, so my plan today is to talk about navigating in virtual environments. As Adam said, I'm a professor of psychology at Iowa State University. I'm also part of the Human-Computer Interaction Graduate Program. It's kind of an interdisciplinary grad program we have here. And so I am interested in psychology and its relationship to virtual reality. I thought I'd start with a quick overview of my background and interests. I do research in virtual reality and I do research in spatial cognition. A good chunk of my research uses virtual reality to study spatial cognitive theory. So using virtual environments to create experimental conditions to study things like spatial memory or how we integrate cues to keep track of where we are as we travel. Another chunk of my research uses spatial cognitive theory to inform user interactions with virtual reality and hopefully improve upon user experience. So to that end, I've studied topics like distance perception in virtual reality, locomotion interfaces, how we get around in virtual reality, balance in virtual reality, which is important when it's used for things like physical therapy, and cyber sickness, which is kind of an undercurrent to all of the research I do using virtual reality. What I'll be telling you about today focuses on this piece here about locomotion interfaces, so interfaces to move through virtual environments. So a quick outline of my talk. I'm going to give you an overview of a little bit of background on locomotion interfaces for virtual environments. I'll then describe 3 experiments looking at the impact of the teleporting interface, which is one of those locomotion interfaces, and environmental cues and how those things combine to impact navigation. I'll then present a 4th experiment that looks at how training impacts performance when using a locomotion interface, and then I'll close with some conclusions, summary, and future directions. So first, a little background on locomotion interfaces for virtual environments. To give you a sense of where this all began, I'm going to ask you to, in just a moment, close your eyes. Now, you're not with me here, so I don't know for sure that you're closing your eyes, but I'll take your word for it. And when you have your eyes closed, I'll describe to you a path that I'll ask you to imagine walking along. And then at the end of that path, I'll ask you to imagine where the start of the path would be from the position at the end of the path, and then to point back to the start. So go ahead and close your eyes for a moment, and I'll describe a simple path. Imagine walking forward 10 feet. Imagine turning to your right 90 degrees, so straight to your right. And then imagine walking forward another 10 feet. And that's the end of the path. Keep your eyes closed and to the best of your ability, point to where the path origin was. You can point with your finger or your hand or something. Okay, so what I'll show you now, you can open your eyes. First, I want to show you the path that I asked you to imagine. So to walk forward, turn to your right, walk forward again. So we should all be able to look at this and agree that from this perspective, the correct judgment is to point back and to the right from the end point of the path. What I find when I give this demonstration in person to a class or an audience is that about half of participants will point in the correct direction, back and to the right. And the other half tend to point back and to the left, a 90-degree error. Now, There are many reasons why people make that specific error in this case, but I want to focus on the fact that if you were to have actually walked this path, physically stood up and walked this path, even with your eyes closed, nobody would point back into the left. Everyone would point in roughly the correct direction, give or take, a little bit of error. And the research that I've done and others have done suggests that what's missing from the imaginary example is the self-motion cues that you normally receive when you walk. So vestibular cues from your ears, proprioceptive cues from your legs, visual cues indicating that you're moving. So I'm going to come back to that repeatedly during this talk, the importance of self-motion cues. First, I want to note that we call this a triangle completion task. You walk 2 outbound path legs and then point back to the beginning, try to complete the triangle. And it's a measure of a spatial cognitive process that we call spatial updating. That's basically how well you can keep track of where you are in space as you move around. So triangle completion, that's the task, and spatial updating is what we think is the process that we're assessing through that task. So, back to the idea of locomotion interfaces for virtual reality. So ideally, virtual reality users would be able to walk and turn to move through a virtual environment. And I say ideally because then all those self-motion cues are available that enable successful spatial updating, keeping track of where you are. However, virtual environments are typically larger than the walkable track space. There are couches, walls, etc. And so we need some kind of a locomotion interface to get around. We can walk in small spaces, but then we need to get farther using an interface. The most obvious way to do this is to use something kind of like a video game interface, like a joystick, where you get smooth visual movement and you're just sitting in your chair or standing. But that kind of interface can cause sickness. We call it cyber sickness, visual motion in virtual reality without the accompanying body cues. There's a sensory conflict theory that describes some of this. So that's not ideal, although people do often use that kind of interface and sometimes can tolerate the sickness or don't get sick at all. But in response to these constraints, teleporting has become one of the primary locomotion interfaces to move around through virtual reality. For those of you who haven't seen what this looks like, I'll show you a quick video here of one type of teleporting interface. Here the user points to where they want to go by positioning that little green disc, and then they're instantly transported upon pressing a button or releasing a button to that position. Now they turn their bodies and their heads in this case to rotate, but to translate, to change position only, they teleport. So when they teleport, they get no self-motion cues. It's just instant. They're transported without any body or visual self-motion cues. Sorry, that's going to play again. We call this particular interface in the video. In my lab, we call this partially concordant teleporting, because I'm going to introduce another kind in a moment. And the reason we use that term is that movement of the self, when it comes to rotations, movement of the self, movement of the body is in agreement with movement through the virtual environment. So that part's in agreement, but when it comes to translation, it's in disagreement, right? So it's partially concordant when we consider the relationship between movement of the self, the physical self, and movement through the virtual environment. I want to contrast that then with what we call discordant teleporting. This is a different kind of teleporting interface where the user now can select both their position and their orientation, and then are teleported to that position and orientation in the environment. So now they've got this disk and these arrows that they manipulate, and they can still turn their head to look around, but all of the navigationally relevant movement happens through the interface, translation and rotation. So now it's discordant because none of the movements through the virtual environment are in agreement with movement of the self. It's purely virtual, nothing physical. There are no self-motion cues. Okay, so there are two different types, two different flavors of the locomotion interface, the teleporting interface. So I'm going to describe now 3 experiments looking at the impact of that interface, and some different kinds of environmental cues and how they affect performance on this triangle completion task that I introduced earlier. So we ask in these experiments, does teleporting negatively affect navigation? We ask whether the virtual environment can be designed to better support navigation. So if I'm designing a virtual environment, what can I do to make it better, less disorienting? And can the user be trained? And I'll get to that in the fourth experiment. Can the user be trained to be a better navigator in the context of this teleporting interface? So some general methods. Participants performed triangle completion tasks repeatedly in VR. It looked a bit like this. They would travel to a sequence of posts, a green post, then a yellow post, then a red post, each of which would disappear upon arrival at that post. And then at the end of the path, when they get to the red post, they have to point back to the green post, the path origin. And one of the main independent variables is the interface that they use to traverse the outbound path. So they could walk, or they could use these two different teleporting interfaces. So first I'll show you a quick video of the task when walking. So there's the green post. It marks the beginning of the path origin. It disappears when they arrive. This is kind of a small path. They then walk to the yellow post. That's the end of the first leg, and now to the red post, which is the end of the second leg. And then they point back to where they think the green post was and press a button, and then they continue on to the next trial. Here's the same task using the partially concordant teleporting interface. So here they teleport to translate. So they position these little circles to say where they want to go, and then they're instantly repositioned, but then they rotate their bodies to turn. So they have the rotational self-motion cues, but then they respond in just the same way as they did when they in the walking condition by pointing back to the path origin. And then finally, the discordant teleporting interface. Our implementation of it had this big purple arrow that they would position and orient. And this is where those markers at the base of the posts come into play. Those specify the direction of the next post in the sequence. They are necessary for the discordant interface because you have to tell them where to orient themselves to upon teleporting. So now there's no self-motion cues along the outbound path, but then they turn and point to the path origin just like they do in the other two conditions. So 3 different interfaces for the outbound path. The turn angle is manipulated. It's not a really important variable, but one to keep the triangles different as they do repeated trials. We also manipulate the relative lengths of the path legs. I won't be talking much about those at all about those variables, but they're there. The primary dependent variable, so what we measure, the performance variable, is their pointing error. The way we define it in the slides I'll show you is the absolute distance between the response location and the correct location, the path origin. So the first experiment, we had these 3 different interfaces: walking, partially concordant teleporting, discordant teleporting, and 2 virtual environments. One was an open field, and you've seen that already in the videos I showed you. There's just nothing there, just grass. And the other environment we used had landmarks, and we thought that ought to be to the benefit of the navigator. The landmarks environment, and I'll show it to you here, had some distal landmarks that were kind of like marking the cardinal directions almost. So landmarks off in the distance, plus some more proximal landmarks. They were all pushed away from the walking space, but they're around. There was a big tree, that's kind of the main one, and the tent and some other things around there too. So they have landmarks in that case, which presumably should be beneficial. So here are the data for the first experiment. On the y-axis is absolute error. So higher is worse. That's the distance between their response and the correct location. On the x-axis are the 3 interfaces. So walking on the left, partially concordant teleporting in the middle. That's where they can rotate their bodies, but teleport to translate. And then discordant teleporting on the right. That's where they teleport to translate and rotate. The first thing you can see is that, that there's this really clear effect of the interface. Walking is best. Partially concordant teleporting is a little bit worse than walking. Discordant teleporting is a little worse than that. This is really an effect of self-motion cues. You remove self-motion cues, people get lost. The the two colors of bars, this was really surprising to us, and probably is to you too. The landmarks didn't help at all, and we really puzzled a lot over this. We thought for sure the landmarks are going to help. Maybe they'll eliminate the cost of teleporting. We weren't sure, but here they're clearly not helping. There are a lot of reasons that we speculated about as to why that might be. We thought perhaps people aren't paying attention to the landmarks. We thought maybe the landmarks are too far away to be useful, although that's not obvious why that would be a problem. But the landmarks were kind of randomly arranged. They aren't structured in any way. Maybe that's a little disorienting. We've traced down some of these things, but I want to highlight what we think is the main issue, and that is that there are no boundaries. Research in spatial cognition and animal and human neuroscience highlights a really important role for spatial boundaries that kind of anchor our bodies into a space. And so I'm going to show you a follow-up experiment to this where we added boundaries. Before I get to that, here's one thing that some of you might wonder about. Performance in the slide that I showed you here. It's hard to know how well they should be doing or how bad they are doing in the worst case scenario. Another way to say that is what's chance performance, right? Are they doing better than chance in the discordant interface? And they are, not a lot better, but they are. And one way to look at that is to look only at angular error. So when we quantify performance as angular error, and here it's absolute angular error, we can work out that chance performance, just random pointing, would lead to 90-degree absolute angular error. So 90 degrees in this figure would be chance performance, and they're all better than chance. You can see they're not doing great in the discordant interface, but they're doing better than chance on average. Okay, so back to the idea about boundaries. So here's a follow-up experiment where we thought, if boundaries are important to spatial updating, to keeping track of where you are, then adding a rectangular fence into the landmarks environment could be of benefit, right? It might now be a useful cue. Now we've done some follow-up studies where we do just the fence and not the landmarks, and I can talk more about that later. But for this study, we compared those same three interfaces, walking and the two teleporting interfaces, in two environments, what we call the fence plus landmarks environment, and I'll show you that here. So here's basically the same landmarks environment, but we've added in a square fence. It's a low fence, so you can see all the landmarks past it, but it adds a boundary that encloses the space. But otherwise, the task is the same. And we compared this to an open field, empty grass field. So here are the data from this experiment, and the patterns look a bit different. On the one hand, here's what's the same. The effective interface, you still see going from left to right, worse performance as we remove self-motion cues through the teleporting interfaces. But what's different is that the consequences of removing those cues is mitigated when we put people into this fence and landmarks environment. So the landmarks on their own weren't helpful, but adding in the fence is beneficial. Now it turns out the fence by itself is also pretty helpful, although the landmarks can be useful. And we've done some follow-up work that I can talk about later in the discussion if you're interested, where we've come to the conclusion that the landmarks are useful, particularly for disambiguating the boundaries. So if there's an ambiguous boundary like a circle or something, it can be beneficial for that. So boundaries do seem particularly important. So one of our goals is to give designers some ideas as to how they should create virtual environments that are less disorienting. So we can say, well, you ought to include boundaries in your environment. Now, that's not particularly specific. Um, and one of the reasons, one of the ways we could be more specific is to describe what kind of boundary is helpful. You could imagine boundaries could be a fence or a wall, but they could also be a drop-off, or maybe even just a rug on the floor that defines a space, like at a restaurant or something, or in a living room. And we were interested in further understanding what makes a useful boundary. So that brings me to our third experiment. This is one that we recently submitted for publication. Um, Here we asked what constitutes a useful boundary, and we had a few different conditions that we wanted to compare. We had the open field that had no cues to it, the one that we've used in the past. We had a drop-off environment where the boundary was a cliff. So they're on this platform and there's a drop-off boundary. Um, we had an environment where the boundary was defined by just a change in the texture on the ground plane. That is to say, a discontinuity like a rug basically, but on a flat floor. We used an environment where the boundary was defined by the fence, the same fence I showed you before, minus all the landmarks. And then we had kind of a best case scenario environment. This is one that we've used in other studies and we know people are pretty good at. It's a virtual classroom that has rectangular walls. It also has a lot of landmarks. So a big blackboard on one wall, a door on another wall, windows on another wall. In some ways, this is like, yeah, best case scenario for boundaries plus a bunch of stuff. So that kind of bookend that between that and the open field, it kind of bookends the performance at best and worst case scenario. Now for this study, we had so many environments we wanted to compare that, and this was all repeated measures within participant design. So we ended up excluding the walking interface because we just didn't have enough trials. It was just gonna be too many trials. So we kept the two teleporting interfaces, dropped the walking interface. Now, I'm going to ask you to reorient here to this figure. I apologize. We've laid this one out differently than the others. And the reason is that now the primary variable of interest is the environment. And that's what you'll see on the x-axis. So the open field on the left, and then the drop-off, the fence, the texture and discontinuity, the one that's sort of like a rug on the floor, and then the classroom on the right. And now the colors of bars correspond to the two teleporting interfaces. So I guess the first thing I should point out, and there's no text on this, is that the partially concordant interface is better. People perform better with that than with the discordant interface. So that is to say, when they have rotational cues, just like we saw before, they do better. What we were most interested in is the effect of the environment. And so the open field performance was the worst. In the classroom, performance was best. And then the other three that have a single boundary that's defined in different ways are essentially the same. The caveat is that the drop-off environment did perform a little bit worse with that one, the discordant interface. I don't have a great reason for why, but I'll add that I'll note that that it's a pretty small difference there. So our general conclusion here is that basically any boundary will do. Any boundary is a useful boundary. Furthermore, supplementing boundaries with additional cues, like in the classroom, is best, right? So adding in landmarks like the blackboard and other things that distinguish the boundaries, further distinguish them, is even better. Okay, so the fourth and final experiment. Another thing we're interested in is, in thinking about how to make the user's experience better, we can of course affect the environment by designing an environment that's less disorienting. But perhaps there are also things we can do to help train the user to be so that they will become less disoriented and therefore have a better experience in VR. So in this experiment, we looked at whether training would lead to better performance. In particular, what I mean by training, I guess I mean two things. One is practice, and the other is feedback. So practice plus feedback about your performance and that might allow you to improve. So in this experiment, we asked, does navigation performance when teleporting improve with practice and with feedback? Now, this was a study that we conducted during the pandemic, and we decided to do something different. Normally, we recruit participants by bringing them into the lab. Most of them don't have much or any VR experience. In this study, to reduce contact between participants and experimenters, we did this online. We recruited participants who own a VR headset, so they have VR experience. Um, I'll come back to that later. Um, Participants, all participants completed 3 blocks of triangle completion trials. So you can see this illustrated at the bottom. Block 1, they completed 12 triangle completion trials without any feedback, so no indication of how well they're doing. And then in block 2, there were 2 conditions that participants were split into. Participants in the feedback condition completed 24 triangle completion trials with performance-based feedback that I'll show you what that looked like on the next slide. And then the other half of participants in the no feedback condition completed 24 triangle completion trials that gave no feedback, and they looked identical to the block 1 trials essentially from the participants' perspective. And then finally, block 3 trials, again 12 repeated trials with no feedback. So we thought that if feedback is, if practice is beneficial, then we should see block 3 performance is better than block 1 performance for both groups of participants. If feedback is important or beneficial on top of practice, then we should see that that improvement from block 1 to block 3 is greater for participants in the feedback group compared to the no feedback group. We also had 2 teleporting interfaces, the partially concordant and discordant interface. That was manipulated for the first time compared to the previous experiments I described. The interface manipulation was between participants. Half of participants did one interface, half did the other. And the reason was that we were looking at practice and feedback, and we thought we might get some weird carryover effects if we had people do one interface first and then the other. So that was between participants. So here's a look at the feedback that participants received during block 2 if they were in the feedback condition. So this is the view, the participant's view from the end of the path. They've reached the end of the path, they've pointed to where they think the path origin was, and then they see, after they choose their response, they see their answer, that's the blue post, that's their answer of where they thought the path origin was. They also see the green post, that's the true location of the path origin that they were trying to point to. And then they also see a circle that represents their average error over those 24 feedback trials. So on the first trial, the circle's the same as whatever the distance of their response was from the green post. And then if they're able to improve over 24 trials with feedback, they should see that circle get smaller. We added this partly as just kind of additional feedback, but also to maybe motivate participants to try to improve as they go through those 24 trials. Okay, so here I'm going to show you again on the y-axis, this is the absolute distance error of their response from the path origin. These are data. Oh, darn. These are data for the discordant teleporting interface. Uh, the darn was that that little glyph at the bottom is the wrong one. But these are data from the discordant teleporting interface, the more difficult teleporting interface. Those who received feedback, the green bars, improved from block 1 to block 3. So feedback and practice together benefit performance. They get better. Their errors get smaller. In the no feedback condition with the discordant interface, it looks like they're getting a little better, and they are. It's marginally significant. So practice alone without feedback, we think that if we had enough participants in this study, there's probably a real effect there, but it's marginal, it's small, but they do get a little bit better with practice alone. So then I want to show on the right the data from the partially concordant interface. This is the one where they rotate the body at the turn, but teleport to translate. So yellow bars, these are participants who received feedback, and they also improve from block 1 to block 3. So practice combined with feedback leads to improvement in triangle completion performance with this interface. The gray bars are the partially concordant interface where feedback was not provided, so this is practice only. And again, we found a marginally significant improvement from block 1 to block 3. Again, we think there's probably a real effect of practice, but it's small compared to that of the effect of feedback. So those are some new data that we're also just, it says under review. We just submitted it, I think, or we're about to submit it. So those are the 4 experiments I wanted to share with you today. I want to highlight some kind of key findings and summary and talk about future directions for this work. We're at the tail end of NSF project that funded this work, and so we've done almost maybe a dozen studies on this, maybe more. So this is just a little subset. So I'm happy to talk more about other directions we've pursued. So to close, I want to return to some of the questions I began with. Does teleporting negatively affect navigation? Clearly, the answer is yes, right? Walking is better than teleporting, and if you're going to teleport, you're better off having the rotational cues in the partially concordant interface. So teleporting to change your orientation and your position is worse than teleporting to change position only. So best avoided when possible. Now, it may not always be something you can avoid. For example, a user might be seated on an airplane or have a mobility impairment that prevents them from physically rotating their bodies. And so in that case, they can't use the partially concordant interface. But there's still hope because it turns out that the virtual environment also can be designed to better support navigation, even if you have to use a challenging interface. So environmental boundaries mitigate the consequences of using difficult locomotion interfaces. We found that any boundary, well, of those we tested, any boundary is a useful boundary. The flooring pattern was even useful. Walls, a drop-off. Landmarks are useful, but only to an extent. They're useful especially when they're used in conjunction with boundaries. They can help disambiguate boundaries. And then the last question was, can the user be trained to be a better navigator? Clearly, they improved. Triangle completion performance improved with feedback-based training. Practice alone may be somewhat helpful, but the feedback is especially helpful. So I want to highlight a couple things about this. One is that I want to remind you that the participants in that last study were VR owners. So they had some expertise and at least some practice with these interfaces just through their own experience. And that further goes to show that practice alone may not be all that beneficial, because there was room for improvement through feedback. Um, Other things we're interested in, though, and I'll get to this more in the future direction section, is what are the kind of downstream effects of this practice? Right? So if you become better at triangle completion, are you now better at creating a mental map of your space, right? So what are the bigger implications of this kind of a feedback-based training? Okay, so some future directions before I end and open to questions. Um, I find it interesting that there are some uh, interfaces that blend teleporting with kind of free locomotion, joystick locomotion, and they seem not to dramatically increase sickness. So here's an example of an interface where you teleport by selecting where you want to travel, but then you get this fast, um, uh, constant speed, no acceleration, deceleration, visual locomotion through the environment. Um, is that beneficial to spatial updating? It's an open question. It's likely that it's beneficial to at least things like presence and user experience. I mentioned, the locomotion interface is designed, the teleporting interface is designed to reduce sickness. Well, there are other comfort settings kind of to mitigate cyber sickness that are popular, like the blinders that are often popular in VR games where it reduces your peripheral vision while you're traveling. That also reduces cyber sickness. I'm interested in the impact of that on spatial updating. It's unknown whether that has any negative consequences. We're interested in more complex cognitive tasks like cognitive map formation, right? How do we learn a complicated space? And so we've done some early work on this. Here's a map someone drew after exploring an environment, and we're interested in how these different interfaces impact cognitive maps. And recently, I've become very interested in cyber sickness in and of itself. We've been doing some research. Here's a game where what we've been using in my lab. It's just an off-the-shelf consumer video game, Jurassic World. It's a VR game, and you primarily navigate with a joystick. And it makes people feel pretty sick after around 10 to 15 minutes. They rate their sickness as like 6 or 7 out of 10. And so we're interested in understanding cyber sickness. How significant is it? Do people adapt? Right. So if you experience this repeatedly, does your experience of sickness diminish over time? And related questions to that. So it's another interest of mine related to locomotion interfaces. Lastly, I want to close by thanking collaborators, graduate students, faculty here at Iowa State. We've had a number of people involved. I also want to acknowledge the National Science Foundation. This is the end now. I think this is the end of our 4th year on the project, and the project's ending, but we've had a lot of fun on it. So I hope you enjoyed the talk, and I'm excited to answer any questions. Thank you.
Okay, thank you, John. That was a great talk. I really enjoyed it. So, for those folks watching remotely, post your questions to the chat in the live stream, and we'll answer those as they come up. So, John, while we're waiting on some folks to ask questions, uh, you know, there's when you run studies in with humans just in general. I was going to say in VR, but with humans in general, you see a fair amount of variability depending on the task between your subjects. Did you have any observations about individual differences for these navigation tasks?
Absolutely. Yeah. One thing that I find really striking in research on spatial cognition is the vast individual differences. Uh, they're pretty dramatic, really. And And the same is true in the cybersickness research we've been doing. But in spatial cognition, individual differences are really prominent, and it's a big area of research in just kind of basic spatial cognition. In these tasks, and hopefully you'll still be able to see these. Um, oh darn, I don't have it. In these tasks, we have um, quite a range of performance, a small range when walking. So performance when walking is pretty constant. But when you add in the teleporting interface, we see this really big distribution in errors. And it's interesting to think that some people seem to be almost unaffected by the removal of self-motion cues, and other people are horribly affected by it. And so one of the things that we're interested in, and this gets back to the training piece as well, is identifying people who are likely to be disoriented. Partly so we could steer them to a better interface. Let's say if we can identify through spatial tests that they're going to do poorly at using the discordant interface, we'd say, hey, maybe you ought to try walking or doing one of these other things. But also we could identify people who would likely benefit most from training. And so with the identification piece, we've found that there's a test that seems most diagnostic, predictive of people's ability to to do the triangle completion task when teleporting, and it's a test of perspective taking, where you're asked to imagine different perspectives within an array of objects that you see on the screen. And people who do better at that tend to do better at the teleporting triangle completion task. So that's something we've been actively exploring.
Cool, cool. We have a question in the chat. How similar is cyber sickness to the kind of sickness you'd feel after riding amusement park rides?
Yeah, this is a really interesting question. So the literature, and this is kind of a new research domain for me, but as I understand it, there's this huge motion sickness literature. You know, seasickness, the roller coaster, all kinds of things like that. And what defines motion sickness in those cases is movement of the body, right? There's motion. Whereas cyber sickness, the motion is visual. The body is still. And that, in fact, that sensory conflict may be one of the main contributors to the experience of sickness. So, um, in the case of the roller coaster, that's a little tricky because in that case, you get lots of visual motion and you get all this body motion. There are a lot of other cases of motion sickness that are more comparable to cyber sickness. So, like, I get sick if I read in the car. So if I've got a book or my phone and I'm looking down in the car and the car is moving as I'm reading, my body's moving, but my visual system has this static visual world. And so there's a sensory conflict. The sensory conflict in cyber sickness is similar, except it's flipped, right? So the visual world is moving, the body is still, but that conflict still persists. It doesn't fully answer the question about the roller coaster, but I do think that it's closely related, cyber sickness and motion sickness, and certainly the symptoms of those things are quite similar: nausea, disorientation, those kinds of things.
All right, I've got a question for you. So looking back at the influence of boundaries on the triangle completion task, uh, you had now none of these are physical boundaries, but I'm going to refer to some of them as physical because they geometric boundaries. We'll call them that. Okay.
I like it.
Okay. So you have geometric boundaries and you have textural boundaries. Um, so I can't remember off the top of my head the studies looking at this, but I seem to recall that there's some evidence indicating that we process geometric boundaries and textural boundaries differently internally. Uh, do you think it's the same causal mechanism in your study in providing the benefit for these two conditions, or do you think it might be getting benefit from two different things happening internally?
Yeah, I find that this is a great question. I find this really fascinating. So some of the boundaries are, you know, impediments to your navigation, and others, like the texture in particular, is just a visual thing. Well, all of them are just visual,
Yeah.
as you correctly stated, but they may not feel that way to the person in VR. And so there's some really interesting neuroscience literature on this. Um, Unfortunately, much of it falls into the animal neuroscience domain, and I hesitate when trying to draw parallels between those, between animal research and human research. But I'll tell you what I know about the animal literature. In animals and also recently in humans, there's a type of neuron called a boundary vector cell. There's other names for it, but it's part of this complex set of neural hardware that helps you orient in space. And those boundary vector cells, what they do is they represent the distance and direction to boundaries. And it's like, aha, this seems like exactly what would be important in these kinds of tasks. Um, and and what we know is that those boundary vector cells in animals are especially prominent. They respond strongly to these navigational impediments, like a wall or a drop off. Um, they respond more weakly to texture boundaries, just pure visual change. And there's similar research in humans that suggests that there are differences in how we process boundaries that are navigational impediments versus just visual transitions. Um, and so I would say there's a chance that there's a different mechanism that makes the carpet a useful boundary compared to the wall. Um, one other one other anecdote, tangentially related research, is that in Parkinson's disease, there's a phenomenon whereby people with Parkinson's, when they're walking, they sometimes exhibit something called freezing, where they stop walking even though they don't want to. And those freezing events tend to happen at transitions, like going through a doorway, or transitions in texture even can cause freezing. And so that suggests maybe, if that's related to detection of boundaries, perhaps those two kinds of cues, the texture boundaries and the geometric boundaries, are related to other types of behavior, like how we move through space, and that's reflected in Parkinson's disease.
Cool, cool, very cool indeed. All right. I think we're going to wrap it up there. Thank you all for attending today's talk. And John, thank you immensely for coming and speaking with us today. It was great to see you and great to hear about the work that you're doing.
Yeah,
And
thanks so much for
yeah,
inviting me. I enjoyed this.
excellent, excellent. And with that said, we're going to conclude our live stream. Hope everyone's staying happy, healthy, and safe, and we will see you the next time around.